So now we have the pleasure to listen Takahiro, which will speak us of quantum thermodynamics. It was a subject where he was recipient of the Junior Boltzmann Medal 10 years ago.
Thank you.
So it's a pleasure to listen to you.
Thank you. Thank you for your introduction. I'd like to thank the organizers, especially Raphael and Abhishek, for giving me the opportunity to talk in this workshop. Today, I'm talking about thermodynamics of information, especially about quantum thermodynamics with quantum information flow, both theory and experimental perspectives. So this kind of quantum thermodynamics is based on the formulation of quantum trajectories. So I think this topic fits very well with this workshop. Okay, and also I'm a theorist, but I will talk about some experimental collaborations. Okay, so this is the collaborators of this work. The theory side was done by my colleagues in University of Tokyo, and the main contributor is Takahiro Yada. He is my student. And the experimental part was done in Harvard University, Lukin's group, and the platform is SIV Center. So today I will start with some general background of thermodynamics of information, and then I will go to the theory part, and then I will talk about our recent experimental results. Okay, so let me start with a little bit long introduction to this field. Okay, so the very general background is thermodynamics of information. It dates back to the 19th centuries, so-called Maxwell's demons thought experiment. From the modern point of view, thermodynamics of information is connected to the feedback control on thermodynamic systems, because Maxwell's demon can be regarded as a feedback controller on thermodynamic system at thermal or quantum, at the level of thermal or quantum fluctuations. So by this kind of originally very old argument, we can understand the foundation of the second law of thermodynamics, and we can apply it to nanomachines and nanodevices from the modern point of view. Okay, so this is the simplest model of Maxwell's demon, known as the Stellardo engine. So by this engine, so the Maxwell's demon gets one bit of information, that is log 2 of information, and one can extract KT log 2 of work from this isothermal cycle. So this clearly shows the quantitative connection between information and thermodynamics, because log 2 of information is exactly corresponding to KT log 2 of work. And here T is the temperature of the thermal environment. So this can be regarded as the ordinary definition of the free energy, because Maxwell's demon can reduce the entropy of the system by log 2 in this case. And that means that the free energy is increased by KT log 2, and that is a resource of the work. So the important point is that we can control physical entropy by using information. So more precisely, the important information content in classical information theory is known as mutual information. So this quantifies the effective information Maxwell's demon can get from the measurement. In general, there is some measurement error during the measurement process, and the effective information obtained by the measurement is in general smaller than the Shannon information. So the effective information is characterized by the mutual information that is regarded as a correlation between the system and the memory. Memory means some measurement outcome. And this mutual information satisfies these inequalities. It is always greater than 0, and it is smaller than the Shannon information. So this is a basic information quantity to consider the thermodynamics of information. Okay, so in our very old work, so we have derived the upper bound of the work that can be extracted from Maxwell's demon type heat engine. So if there's no Maxwell's demon, the upper bound of the work extracted from a thermal heat bath is bounded by the difference in the free energy. But if there is a Maxwell's demon, the upper bound is enhanced by the mutual information multiplied by the Boltzmann constant and the temperature. So this gives the fundamental upper bound of the capacity of Maxwell's demon. And this bound is achievable. So in that sense, this is a kind of generalized second law of thermodynamics in the presence of information processing like feedback control and measurement. So this is also an old experimental demonstration of Maxwell's demon in 2010. So in this classical setup, we have demonstrated that one can actually extract the work from the feedback protocol, and that is larger than the conventional thermodynamic bound. And also we can quantify the efficiency of the conversion rate from information to energy, and that is, in this case, given by 30%. So, and this old experiment triggers some experimental studies with various platforms from classical to quantum. So there are many experimental realizations of Maxwell's demons in both classical and quantum platforms. In the classical case, colloidal particles and DNA molecules are very interesting platforms. And in the quantum regime, we can use the superconducting qubits or NMR and also many other platforms. Okay, so, and I will introduce next another important background of this work that is known as the fluctuation theorem or the Jarzynski equality. So this was derived in 1997. So, and this is a kind of a generalization of the second law of thermodynamics in terms of equality. In conventional second law of thermodynamics, it is always given by inequality and not exactly equality. But this equality means that if we take into considerations the higher orders of fluctuations, then the second law of thermodynamics is always given by this single equality. And from this, we can derive the standard second law by using some convex inequalities or something like that. And also, we expand this exponential and we stop it at the second order of cumulant, then we can recover the fluctuation dissipation theorem in the linear response theory. So in that sense, this fluctuation theorem is a kind of unified equality that includes many known relations in thermodynamics. Okay, so as I mentioned, from this fluctuation theorem, we can reproduce the second law of thermodynamics. So then the question is, how about the fluctuation theorem in the presence of Maxwell's demon or feedback control? So the answer is, if we consider a kind of stochastic version of the mutual information, then we can still have the fluctuation theorem in the presence of Maxwell's demon. So this I is a stochastic version of mutual information. And if we take into consideration the stochastic mutual information inside the ensemble average, then we still have the same form of the fluctuation theorem. And from this, we can recover the second law of thermodynamics with feedback control. Okay, so anyway, this is very old, I think 15 years old result. And next, I will go to the quantum counterpart of this kind of work. So in the classical case, the mutual information is a relevant quantity. And in the quantum case, the important information content is called the QC mutual information or the Grunewald information. So this was first introduced by Grunewald in 1971. So in the context of quantum measurement theory. So this characterizes the information, a kind of quantum information obtained by some quantum measurement. The meaning of this QC is quantum and classical because the measured system is quantum in this case, but our measurement outcome is classical. So this is a kind of hybrid mutual information between quantum measured system and our classical measurement outcomes. So the formal definition is given by this. This rho is the measured state before the measurement. And this tau of y is a post-measurement state under the condition that our measurement outcome is y. And this is our averaged von Neumann entropy of this post-measurement state. And this difference is given by the QC mutual information. So this can be decomposed into two parts. One is the so-called horrible information that is slightly different from this QC mutual information, because here we have tau. Tau is the average of the post-measurement state, and von Neumann entropy of tau minus this averaged von Neumann entropy. It's a horrible information that gives a correlation between the post-measurement state and the measurement outcomes. But in this case, we have this additional term that describes the entropy change by the measurement, average entropy change by the measurement. And this tau is a post-measurement state on average, and rho is a pre-measurement state. And combining these two terms, we have the definition of the QC mutual information, and that describes a kind of correlation between the pre-measurement state and our measurement outcome. So this is the basic idea of the QC mutual information. And by using this, we can generate the second law of quantum thermodynamics in various setups. A very general formulation is given by this. So first, we need to introduce the concept called the entropy production. That is basically given by the von Neumann entropy change minus the heat exchange between the system and the heat bath. And beta is the inverse temperature of the heat bath. And this can be also written as the difference in the work and the free energy. But here, free energy should be kind of non-equilibrium free energy, defined as the von Neumann entropy minus the average energy. And also, we can introduce the stochastic version of entropy production, especially that stochastic von Neumann entropy is just given by minus log of the diagonal term of the density operator. And also we can introduce the stochastic QC mutual information like this. This is a little complicated, but basically this is the difference in the diagonal term of the post-measurement state under some measurement outcome and the pre-measurement state, the diagonal distribution of the pre-measurement state given by this. By using these quantities, we can show that the lower bound of the entropy production can be negative, and that is bounded by the minus of the QC mutual information like this. And also, by introducing this stochastic QC mutual information inside the ensemble average, and if we take the exponential of minus of entropy production minus QC mutual information, then we always have 1. So this is a generalized fluctuation theory for the quantum measurement setup. Okay, so this is a very general result in previous works, I think already more than 10 years ago. So now our motivation is how to generalize these results to continuous measurement and feedback setups. So that is the main topic of this work. Okay, so next I will go to the theoretical part of this work. Okay, and then let me clarify the motivation of this part. So as mentioned in the previous lecture in this morning, so there are many experimental setups in which we can perform continuous or successive measurement and feedback control. So for example, we can use cavity QED. So this is exactly the same figure as that in this morning, and circuit QED or nanoparticles or something like that. In these systems, we can perform a continuous measurement in time and also feedback control, and we can prepare and stabilize desired quantum states. So the question is how to quantify quantum information flow in such a continuous measurement setup, which is induced by continuous measurement and utilized by continuous feedback control. Okay, so in the classical case, there is a known and maybe standard measure of classical information flow that is known as the transfer entropy. So this is widely used in time series analysis, not necessarily in physics, from neuroscience and financial engineering and biochemistry. So actually this transfer entropy was originally introduced in economics in 1960s, I think, and it won the Nobel Prize. So, but in this context, we use a purely mathematical or information theoretical aspect of transfer entropy, and that is a kind of a conditional mutual information. And then our question is how to quantify quantum transfer entropy and how to relate it to thermodynamic laws. So that is a main question in this work. And also there are many generalizations of the second law of thermodynamics for both for classical and quantum measurement setups. So the simplest one is a classical and single measurement. And in the case of quantum and single measurement, the QC mutual information is a relevant quantity. And also in the classical and continuous measurement setup, we can also generalize the second law of thermodynamics by incorporating the transfer entropy. Now, the question is how about the quantum and continuous setup and how to generalize the second law of thermodynamics and the fluctuation theorem. So that is our main question. Okay, so and this is a summary of our theoretical result. So we can successfully generalize the second law and the fluctuation theorem by incorporating the quantity that we name the QC transfer entropy. I will show the precise definition in the next slide, but so we can introduce a kind of the QC or quantum version of transfer entropy that can quantify a continuous information flow from the quantum system to our classical measurement outcome. So, and at the level of ensemble average, the entropy production is bounded by the minus of the QC transfer entropy, and the fluctuation theorem is also given by almost the same form. Okay, so this is our setup. So here we use the quantum trajectory approach. So we have system, and here's a heat bus. And we have the Lindblad term corresponding to this heat bus effect. And we can consider the unraveling of this heat bus, and we can define the stochastic heat and stochastic entropy production. And also, at the same time, we introduce the measurement apparatus to the system for the continuous measurement process. And that is described by this stochastic master equation here. And this is another stochastic term from the heat bus Lindblad term. And we can add the continuous feedback term that depends on the measurement outcome sequence. Okay, so now we define the QC transfer entropy. So this is basically a kind of accumulation of the conditional QC mutual information. I mean, so in the continuous measurement, and if we discretize it, so we have many measurement outcomes before. And then we consider the QC mutual information between the latest outcome and the system under the condition that we have all of the past measurement outcomes. So that is this conditional QC mutual information. And then we consider the ensemble average over all trajectories of measurement outcomes. And that is the definition of the QC transfer entropy. So this is actually analogous to the definition of the classical transfer entropy. That is a kind of accumulation of the conditional mutual information. Okay, so this is the QC transfer entropy at the level of ensemble average. So, and then next we want to introduce a stochastic or the trajectory version of the QC transfer entropy. For that purpose, we need to introduce another unraveling. I mean, the original stochastic master equation is given by this. So we have the heat bus term and the measurement term. But this is not enough to introduce the stochastic version of the QC transfer entropy because Okay, in the original definition of the stochastic QC mutual information, we need some information about the density matrix itself, because this is the diagonal element of the density matrix before the measurement, and this is a conditional diagonal term after the measurement. To get information about them, so we need to introduce refined unraveling that we named the fine unraveling. So this is the original unraveling. I mean, we have just heat bus term here and the measurement term here. And we can then apply that Trotta decomposition of this, and we can formulate this as an alternative interaction. First, we perform the measurement, and then heat bus introduction, and measurement, and heat bus. And then we insert as a kind of virtual projection measurements before and after this real measurement. And this virtual measurements are regarded as the projection measurements. So in that sense, this is a very strong measurement on the system. And usually we cannot consider such the quantum trajectory for such a strong measurement. But in this case, that is possible because the change of the state or the diagonal element induced by each measurement interaction or heat bus interaction is very small. So this the difference between these two projection measurements is very small. So we can carefully consider the continuous time limit, and we can show that this kind of virtual this kind of sequence of virtual projection measurements is actually very defined even in the continuous time limit. So in that sense, we can consider this fine unraveling. So, and based on that information obtained from these virtual projection measurements, we can introduce the stochastic version of the QC transfer entropy. And by using these terms, we can show that the fluctuation theorem is true even under the continuous measurement and feedback. So that is our main theoretical result. Okay, so the reason why I said these projection measurements are virtual is that, so in real experiment, we can naively think that such a sequence of very strong measurements is not experimentally feasible. So to overcome that point, one simple solution is that we can virtually emulate this kind of time evolution by using a classical computer and virtually get the information about the diagonal term obtained by these strong projection measurements. So that is one solution. But another solution is that, so if we don't take the real continuous time limit, and we, instead of thinking about the continuous measurement, but if we consider only the successive iterative measurement that is in discrete time, so then even in real experiments that we can perform such kind of a strong projection measurement. So that is another solution. So the second one is we don't consider the real continuous time limit, but we just consider the successive measurements in the discrete time formulation. So that second solution is the protocol that we have adapted in our experimental result. So that is the next part of my talk. Okay, so then I will go to our experimental results. Okay, so actually, this all of the experimental part was done in Harvard University, Luking's group, and the platform is the so-called SIV center coupled to diamond nanovacancy. So this enables us to perform weak non-demolition measurement, and they can perform immediate feedback with using FPGA, and the coherence time is very long. So this is a very good platform to investigate quantum thermodynamics. So also there is a kind of heat bath interaction here, but this can be regarded as a kind of beta equals 0 case. So there is no real temperature here, but the presence of this heat bath is very important in the following experimental result. Okay, so first we consider a very simple experimental sequence. The purpose is to stabilize the ground state that is returns 0. So in this experimental platform, so we have some free Hamiltonian here, and we have heat bath here, and and these two are not compatible. So the ground state 0 is not stable in this dynamics. So it is meaningful to stabilize the ground state by using a successive measurement and feedback. So the protocol is very simple. So we perform a measurement to distinguish the ground state and the excited state. And if the state is in the excited state, then we apply the pi pulse and rotate it, and then we get the ground state. But the problem is that the measurement is a weak measurement, and this is not so definite process. I mean, the probability to get the ground state is not always 1. So we perform this again and again iteratively. So and we consider the QC transfer information flow or something like that in this sequence. Okay, so this is the generalized second law in this experimental result. So this red points describe the negative entropy production that is smaller than 0. This means that the feedback is actually working. And these green points describe the lower bound induced by the QC transfer entropy. And actually, we see that the QC transfer entropy is actually bounds the entropy production. Also, we can compute the naive classical transfer entropy in this setup, but it gives a worse bound than the QC transfer entropy. This means that here is some quantum effect, and by incorporating quantum effect, we can see that the QC transfer entropy gives a better bound. Okay, so this is the generalized fluctuation theorem. So if we naively take the ensemble average of exponential of minus sigma, then it deviates from 1 because of the effect of measurement and feedback. But if we take into consideration the stochastic QC transfer entropy term inside the ensemble average, we always get 1 around here. So this means that the generalized fluctuation theorem is actually satisfied in this setup. And again, we can consider a kind of naive classical transfer entropy in this quantum measurement. And then we can see that the ensemble average is deviated from 1. This means that classical transfer entropy is not enough to get the proper dynamics of the proper characterization of this dynamics. So we need the quantum transfer entropy, quantum QC transfer entropy to get the generalized fluctuation. Okay, so this is the first half part of this experimental result, and then I will talk about the role of feedback causal structure. So in this protocol, we just use the latest measurement outcome to decide what to do in the feedback protocol. Then next we consider the case that we use a sequence of past measurement outcomes, and by gathering them, and then we decide what to do in the next step for the feedback control. So in this case can be regarded as a kind of non-Markovian feedback control because we use a sequence of past measurement outcomes. On the other hand, if we use only the latest measurement outcome, it can be called the Markovian feedback control. And then we can theoretically derive a more tight bound, a better bound for the second law of thermodynamics by taking into considerations of the case non-Markovian effect. So I will skip the details of this, the definition. Actually, it is very involved. But anyway, so we have some good quantity that we call a case order information term. And then it gives a better bound than the QC transfer entropy. And it again satisfies the fluctuation theorem. Okay, so this is our case order Markovian feedback protocol. In the Markovian case, in this case, we will stabilize the excited state 1. So in the Markovian case, we distinguish the ground state and the excited state, and that we apply the pi pulse if the state is found in the ground state. On the other hand, in the non-Markovian case, we use all of the last k measurement outcomes, and we perform the pi rotation only when all of that measurement sequence are 0. So this is the non-Markovian feedback protocol. And first, we see that how this feedback works in terms of the occupation probability in the excited state. So this is a Markovian case, k equals 1, and that is not good. But in the case of the k equals 4, that is a fourth order non-Markovian case. The feedback works well, and this probability is closer to 1. And we can also compute the kind of conversion efficiency from the QC transfer entropy to the entropy production. And again, we can see that if we enhance the value of k, that is, if we enhance the non-Markovianity, then we have a better performance of the feedback control. Okay, so these are the generalized second law results. And in the this is a k equals 1 Markovian case. And that is essentially the same as the standard QC transfer entropy argument. On the other hand, for example, in this k equals 4 case, that is a highly non-Markovian case. So these red points gives the entropy production that is negative, and that is more negative than the first order Markovian bound that are given by these purple points. So then we can see that this purple region describes the benefit of the non-Markovianity of feedback control. Okay, so again, this is the generalized fluctuation theorem. So even in the higher non-Markovian case, if we take into consideration the case order Markovian information term, then we have the fluctuation theorem like this. Without that term, the entropy production is very deviated from 1. Okay, so this is the summary of this talk. So in the theory part, we have introduced a measure of quantum information flow that we named the QC transfer entropy. And we have theoretically derived and experimentally verified the second law and the fluctuation theorem under the iterative quantum feedback control. And also we have experimentally quantified the thermodynamic benefit of non-Markovian feedback control. Okay, so that's it. Oh, thank you for your attention.
There is some question here.
Thank you for the very nice talk. When K becomes very, very large,
yeah,
here in the K Markovian feedback, I would say, is it related to Bayesian feedback, which means that it is pure quantum state feedback?
Oh.
Can we imagine something like this or not?
Yeah, that's an interesting point. Yeah, I haven't thought about that, but yes, yeah, if K is very, very large, that will be equivalent to the state-based feedback, I guess. So yeah, and maybe that is an optimal case, like the quantum filtering feedback. I guess so, but I haven't thought about that point.
Okay, thank you.
Yeah, hi. Hi, thank you for the talk. So can you just please help us interpret a little bit what the result means? So the QICT, what is doing the extra bit of the quantum contribution is coming from what? Is it coming from the quantum correlations? So you could do it as a time series, as you mentioned. And then I guess part of the lift that you're doing is that you have quantum states, right?
Yeah, you mean this quantum?
Yeah, so what you're calling quantum effect in any of those local, yeah.
Yes.
So where is this physically coming from? Is it coming from the correlations that are shared, or is it, yeah?
It physically comes from the back action of the measurement. So in the case of the QC mutual information, that is described by the horrible information. That is more standard mutual information. And this is a measurement back action term. In the classical case, we don't have this measurement back action. So we only have the standard mutual information. And what we called classical transfer entropy in our experiment is we just drop this kind of measurement back action term. So then it deviates from the fluctuation theorem. So that means that essentially this quantum effect comes from the measurement back action. So if we drop that kind of back action, then the fluctuation theorem is not satisfied.
Could I just ask one quick follow-up? If you used back action evading measurements, so if you just look up Wiseman or any of the standard textbooks and use BAE measurements, does this term go to zero, like automatically?
Yes, I think so. You mean the system is quantum, but if we
use these commuting measurements, there's a very specific definition for
yes, yes. In that case, that quantum region will vanish. I guess so, yeah.
Yeah, thanks for the talk. In the experiment, do you measure sigma and this IQC separately, like independently? Is it possible to see what it is in the experiment?
Oh, right. So we measured these quantities separately. I mean, from the experimental data. So we have all the information about the quantum state or something like that. So we can reconstruct for example, sigma and the QC transfer entropy from that kind of experimental data. So that can be separately done.
Okay.
Right. We have the full information about it.
I have one more question, which is, do you have any other, for example, a classical analog of this? Because this relation you have entropy greater than or equal to a negative quantity on an average, as I understand. Is there a classical process that has a similar feature?
So sorry.
So on an average, sigma is greater than or equal to a negative number, right? Is there a classical process that has a similar feature?
Yes, yeah. That is a kind of Maxwell's demo effect. So yeah, traditionally there are many classical experiments to reduce the entropy. Yeah.
Okay, thanks.
Please, when you ask question, can you first tell your name in order that we know?
Hi, I'm Abhay. Thanks for a nice talk. Could you go back to the slide where you showed us the three different measures?
This?
The sigma and sigma minus IQT and any the previous one perhaps. Yeah. Could you expect any tighter bound than this, or do you think the QCT already contains all the information you can gain from the measurement?
Oh, you mean the tighter bound than this?
Yeah.
I think there is some tighter bound. For example, in this case, we consider the QC version of the transfer entropy. But in the classical stochastic thermodynamics, it is more common to use so-called information flow. That gives a tighter bound than the classical transfer entropy in the classical case. So in the quantum case, I think the QC information flow gives a tighter bound, I think. Yeah. Also, I think this is not the tightest one. So there can be more tighter bound.
If there is a tighter bound, where is that contribution coming from? As in, do you think this does not exhaust all the information you can gain from measurements?
That's a subtle problem. Even in the classical case, the difference between the transfer entropy and the information flow is not so clear. But in the classical case, it is known that if we use the Kalman filter, that is optimal filtering in the base estimation. If we use the Kalman filter, the transfer entropy and the information flow are equivalent. So in this case, I think a similar thing will happen. For example, if we use the quantum Kalman filtering, then yeah, they are the same or something.
Hi, I'm Prabha. Yeah, I had a naive question about the definition itself. It seems that the back action effect comes as a difference of the entropies of the original density matrix and the one you get post measurement. I was wondering if one could use a relative entropy instead. Are there formulations which use that?
I see. Yeah. In this, okay. So in this case, so if we take this definition, so the QC meter information has good properties, like it is non-negative or something like that. If we replace this as by the relative entropy, I'm not sure, but it can work in some way, I guess. Yeah.
So the motivation is to ask if relative entropy can capture some additional correlations which may be missing in this formulation. So.
Yeah, maybe. I'm not sure, but yeah, it's an interesting question. Yeah.
Thanks.
Thanks very much. There is no other question.
Thank you very much.